So let's talk about section 6.3, the solutions of polynomial equations. We're going to learn how to solve polynomial equations by factoring, by grouping, and the root method. We're also going to look about how to find the factors, zeros, and x-intercepts and solutions. We're going to learn how to maybe use technology to even estimate these if we need to, okay? So the first thing is terminology. And say you've got x minus a as a factor, okay? A being some number, okay? We're going to assume that it's positive or negative, okay? But if a is a zero of the function, a is also a real solution of the equation for when the function equals 0, or a is also called an x-intercept of the graph of our y equals f of x, which if it's an x-intercept, that means that the graph crosses or touches the x-axis at that point a comma 0. Now again, all this comes back to the fact that x minus a will be the factor. So let's find the following zeros of the following function. Okay, first off, when you read this problem, when it says find the zeros of a function, that should be the first key words that you're looking for here. Now I'm looking at one that's a little nice here. So f of x equals x minus 2 times the quantity of x plus 5 times the quantity of 3x minus 1. So the keyword, since they said the word zeros, this automatically lets me know that the zeros of the functions, that this whole thing will be set equal to 0, the entire polynomial. Now, the second thing that I know is that because I have this in nice, pretty factored form here, and that's the part that you want to make sure to make note of, is the fact that it's in this factored form. And this is the only time you can do this. If it's got full factors here, so everything is in a set of parentheses and being multiplied to different things, and it equals 0. If everything equals 0, then what we can do is we can just still put every single one of these factors set equal to 0. From here, you'll notice they all look very linear. So taking us back to our earlier chapter 1, we could solve this out and say, oh, well, we have x equals 2 by adding 2 over. Here we can subtract 5, and we've got x equals negative 5. And then here we can add 1, then divide by 3, and we've got x equals 1/3. Now, all three of these answers are your answers. So your zeros of the function are basically x equals 2, negative 5, and 1/3. Okay, all of them are that way. Okay, they can also be written as ordered pairs. So they might just say, if there's no like x equals outside the box, you might put them all in and say, okay, well, I have the ordered pair 2, 0. I have the ordered pair comment between my ordered pairs, negative 5, 0. And then I have also the ordered pair 1/3, 0. Again, why do I know that all of them have a y value of 0? Because, guys, that's literally what we set it equal to, because it said that it was the 0 of the function. 0 of the function means it's some x value that you can plug in that makes the whole thing become 0 for the y value. Okay, these are the two different ways that you will see in which you might write zeros of the function. So if it's got an x equals outside the box, or just asks you to write the x coordinate, then this is all you have to write. But if it asks you to write them as ordered pairs, each x value is its own ordered pair. Okay. All right, so there it is, a little bit cleaner. And again, you've got two different ways that the answers can be written, but these are what we call the zeros of the function. So let's try this again. So what if I give you p of x is equal to x minus 1 times x plus 2 times x plus 5? And I ask you to find the zeros of the polynomial. Now notice I didn't say the word function this time, but I said polynomial. Again, it's the same process. The fact that it says the word 0 here, that means I'm going to take the whole factored form of everything that we see here and set it equal to 0. Now, again, each factor, because it's in factored form, gets set equal to 0. Now, again, remind yourself back to like elementary school. We learned that a factor times a factor equals your number that you might have. And this is why we call something like the greatest common factor means the multiple that they might share in common. So normally when you thought of factors in elementary school, you would say, like, say if you have 3 times 5 equals 15, a 3 and a 5 are factors of 15, okay? But now that we're in algebra style and dealing with variables, every single one of these things in the whole set of parentheses is considered your factor there. Okay, so now that we've set each one of those equal to 0, we can go forth and just solve out, okay? Now, again, a lot of the times you will not see, starting from here on out, they won't necessarily write that whole adding 1 over. So if you need it, go ahead and write it down. Okay, subtract the 2 over, and we get x equals -2. Here I can subtract my 5 over. Okay, and we get x equals -5. Okay, all three are going to be my answer here. 1, -2, and 5. Now, if I change the words up a little bit and say, okay, using the same polynomial, the quantity of x minus 1 times the quantity of x plus 2 times the quantity of x plus 5. And I ask you to find the solutions of where the polynomial equals 0. So notice instead of this time saying the zeros of the polynomial, I say the solutions to where the polynomial equals 0. This again is that same process, but the words are slightly different. Okay, so previously I said the words zeros of the polynomial, and here I say solutions for where the polynomial equals 0. But no matter how I word the instructions here, each single time here, I'm going to set that polynomial and each one of its individual factors equal to 0 and solve out. And again, we still get x equals 1, x equals -2, and x equals -5. Okay, so let me change the words again. Same polynomial. Find the x-intercepts of the graph. Okay, now this is using a word that we started this course with, an x-intercepts. Now remember, an x-intercept, basically our step process that we learned to find x-intercepts was plug in y equals 0 and solve for x. That was what I said back early in chapter 1. Now, instead of it being a y value here, we use our function notation. So remember that this whole thing here, this is y. So basically, I'm telling you when I say find the x-intercepts, that's just another fancy way of saying find me the zeros of the function or find me the solutions of the function. Okay, all three of these are actually the exact same steps. Make sure that the function itself is fully factored out and set it equal to 0. Then set each one of those factors equal to 0 and solve. And there you have it. Again, no matter what direction I use there to work my way through this, each single one of these ended up being very similar in the solving mechanisms that we were doing here, okay? So just keep that in mind as you're working your way through these with those, okay? So no matter which way, whether I said 0 solution or x-intercept, all of them came out with the exact same answer. Okay, now, if you look at the graph of all these, I want you to notice that even though we got the same 3 answers each single time, whether I use the word 0 solutions of where the function equals 0 or x-intercepts, I could have also used my graphing calculator or graphed it, and I could have said, okay, take a look here and I can see where it crosses the x-axis. Notice where it's crossing or touching the x-axis. I'm getting it at x equals 1. So there's my x equals 1. Here's that lovely x equals -2. And here is that final one, x equals -5. So again, all three different ways there. So let's say I've given the x-intercepts of the function are 8, 0, -1, 0, and 3, 0. What are the factors of the function? Okay, so we just found that if something was an x-intercept or AKA a 0 of a function, either way, x-intercept, 0 of the function, I can change out these words both ways, okay? So think of that there. Then that basically meant we solved it all the way out for like x equals 8, x equals -1, and x equals 3. Now let's move that back over. So I'm going to subtract it to bring it back over here so I make it equal 0 because I want you to see this process, okay? So again, I'm subtracting 8 back over so it can be that x minus 8 equals 0. Here I'm going to add my 1 over, which is going to give me x plus 1 equals 0. Here I'm going to subtract my 3 over and giving an x minus 3 equals 0. And remember, if we had all of these to be able to have it fully in this like equal 0, then ladies and gentlemen, that's a factor. So this means this has got to be the factor. This one had to have this factor, and this one had to have this factor, and the whole thing would have equaled 0. So my polynomial function that I would have had in order for these x-intercepts or zeros of the function could have looked something like this. Was an x minus 8, an x plus 1, and an x minus 3. Okay, let's continue. Now, where is this actually useful? Well, what if I gave you something like a box and it's formed by cutting a square of x inches per side from each corner of a square piece of cardboard? Now, that is basically the cardboard is 24 inches on each side. It's a square, so remember squares, all sides are the same. And this will give you a box whose height is x. I don't know how much I'm cutting out just yet. Now, with the length of each side, okay, to the bottom is 2x less than the original length of the cardboard. Now we're going to use volume, which is length times width times height, because that's for a 3D object of a box. Okay, we can say that the volume basically is 24 minus 2x times the quantity of 24 minus 2x times x. Okay, now x again is the amount that we're cutting out. Now again, this is kind of how we come up with it, but maybe if you're a visual person, maybe this might help you. So we literally have a cardboard piece. So this whole thing is 24, but we're taking out a little bit of x here. We're cutting that out and we're cutting this out. And again, this is still x, okay? So we're making a cut here that says x, a cut here that's x, which means this part right here is no longer 24. From here to here is 24. But I'm taking out a little bit of x here and a little bit of x here, which is where I get my 24 minus 2x. So if I were to fold this along these lines and fold it up, okay, so take this and throw it away. We're going to cut this out and throw it away, cut this out and throw it away, and cut this out and throw it away. We can actually fold the box up, and that this side here is that x that we cut out. And this is going to be that 24 minus 2x, and the same thing on this side. Okay, so we're going to take that and we're going to use the factors of our volume, which is already in factored form there. And we're going to find the values of x that give the volume to equal 0. Okay, we're also going to graph it. Okay, and we're going to kind of give the volume as a function and look at all the different things, what values x could possibly be, and we're going to what input values make sense for this problem, and then we're going to graph it and we're going to maybe determine what would give the maximum volume for us. So the first thing we have is we had that factored form that we created. Now we're going to use what we call the zero product property, which basically means that basically if you have two things that are multiplied and it equals 0, that means either A has to be 0 or B has to be 0 or both. Okay. So it could be one or even both. It doesn't matter. It's basically the zero factor property is what we were using at the very, very beginning. So I'm basically going to take each one of these factors and set it equal to 0. Now you'll notice that that 24 minus 2x, I'm only going to write it one time. And the reason being is if I say over here 24 minus 2x again equal to 0 and I solve it all out, I'm just going to get the same answer again, which is x equals 12. So there's no point in doing the same factor multiple times. We can just write the factor one time and get that one answer because it's just going to mean that 12 is going to show up twice. So we get x equals 0 and x equals 12 when we solve it out. Now, if you're unsure where that x equals 0 came from, that's this factor here. So even though there's no parentheses around this factor, it's still being multiplied to the parentheses, so it's also a factor. So we have two possibilities for when the volume will end up becoming 0 is when x equals 0 or x equals 12. So if I were to put that all in the graph, fin calculator and graph it, this is what the graph will look like. And you'll notice here, there's where that x equals 0, and that's where that x equals 12. Okay. Now, what we do notice is that if I were to multiply out all the top terms here, so let me go ahead and multiply out a negative 2x times a negative 2x times x. Now, again, I'm taking each factor and looking for its highest term in each factor. And if I multiply all that out, I get a positive 4x to the third, which means this is degree 3. Okay, it's got a positive coefficient, which means I should, because it's degree 3, I should end on a happy note. So notice it's going up here and down here. Okay, now remember C was asking me what makes sense. Okay, so what values of x? This is a word problem that we started with. Okay, and we created this nice, beautiful kind of volume function. But just because we created this volume function, all the x values may not necessarily make sense, if that is the idea there. So what that's going to do is I'm going to literally just remind myself that x was how much I cut out of our original square. Now our square was originally 24, but I'm going to cut an x out on either side. So what values or inputs make sense for this? Well, just even looking at this, our values basically have to be where x is smaller than 12, okay, or greater than 0. If it's smaller, first of all, you can't cut smaller than 0, okay, because you can't cut negatively into something. So 0 is going to be the smallest value x could even be. Basically, you choose not to cut. However, we need to cut something in order for it to be a box. So that's why I say it's got to be between 0 and 12. Now, why is 12 the limit there? Because, I mean, we can see on the graph here that the volume does go up here, but this part of the volume is not going to exist because, again, our original box, so remember this was 24 by 24. If I were to take, and let me change the color of my pen, and maybe that might visually show this. If I'm going to cut this side here and say I cut 13 here, I'm going to have to do the same cut on this side, which is 13. They're going to overlap. And if they overlap, because I only have 24 inches to cut out of, 13 plus 13 is 26. So they overlap, which means technically you're not actually cutting 13 from either side. So the only way that that will work is if you actually only cut, say, 12. Now, if I cut 12 on either side there, so if I cut here 12 and I cut here 12, you've literally cut 24 by 24, and when you fold it, you don't have a box anymore. So it's got to be slightly less than 12, but it's got to be slightly bigger than 0. So when you fold it, you still have your box. Okay. Now my question is basically what is the next part, which was D, what is the maximum volume? Okay. So realistically, half the graph doesn't even exist. Only from 0 to 12 is what makes sense in the word problem. If this was just a function, I could look at the whole thing. So from 0 to 12 is only what exists for the word problem part. And where would our maximum be? Now remember, maximums occur at the top of the hill. Now, how do I go find that maximum? Well, ladies and gentlemen, this is where you're going to go into that calculator and do second, trace, go to the left of it just slightly, go to the right of it just slightly, and then type in your guess there. Okay. So by using that maximum part in the calculator, we let the calculator do our work for us, and it's going to spit back out x equals 4 and y equals 1024. Now remember, x represents basically how much I'm cutting on either side. So realistically, when I look at this box, again, we started with 24 here, I'm going to cut out 4 by 4 here, and I'm going to cut out 4 by 4 here. Okay, so we're going to cut those, throw them away, cut those, throw them away. Now, originally it was 24. So that means that when I cut out on either side here, from here to here is actually 24 minus 8, because 2 times 4 is 8, which gives us 16. So realistically, when I look at our box there, and I'm not perfect at drawing in 3D, but this is going to be 16. This will be 16, but our height of the box, because we're going to put it up there, is going to be 4. And when you take 4 times 16 times 16, which is how we find volume, length times width times height, it's going to be 1024. And that's the maximum volume of it. Now, granted, I could have chosen to cut something else besides 4, but we want to maximize. We wanted to maximize the volume there. Okay, so what if I gave you something else? Okay, so the amount of Y, photosynthesis, that takes place in a certain plant depends on X of light, which we'll call lumens is how we measure light, according to the following function, 120x squared minus 20x to the third. Now, the model is valid only for the non-negative X values that produce a positive amount of photosynthesis. Okay, so we're going to graph the function first to where we can see a large enough for 2 turning points. Now I know there's got to be at least 2 turning points, or at most, sorry, 2 turning points, because this is degree 3. And then we're going to use factors to find our x-intercepts, and then what non-negative values of x gives us those positive photosynthesis, and then take a look at how to view the graph a slightly different way. So if I'm going to graph this, this is what it's going to look like. And again, I know that, take a peek at the function. Again, 120x squared minus 20x to the third, okay? So our function itself there, 120x squared minus 20x to the third degree, with a leading coefficient of -20, which means I end on a negative note, but I have to start off up high because it's degree 3, which one side up, one side down. And we can see there that we've got 2 turns there. Now, this is also one that if you're putting in the graphing calculator, you may not actually see everything. So when you originally graph it, you guys are probably seeing like a little blip here and here, and then a blip here. So you actually have to really adjust that window to see everything there. Okay, so we've adjusted it. We now see our turning points. Let's factor to find the x-intercepts. Now, in our case here, we're not going to look at the graph and factor backwards because we know one of them is 0 and we know one is going to be 6. However, I've already got a function given to me, so I actually want to factor using the function itself. So the first thing hopefully you see is that they share a common factor. So both of these numbers look like 20 is in common with both of them. So I want to pull out a 20. They also both share the letter x. So I want to take the one with the lowest power, which is x squared. And when I factor that out, I'm left with 6 minus x. Again, I'm going to set it equal to 0 because we're solving to find actually what those factors actually equal. So I have 20x squared equals 0, and then a 6 minus x equals 0. And when I solve that out, I'm going to get an x equals 0 and an x equals 6. If you're unsure on this one here, guys, just notice that if you just add x to the other side, okay, then you get that x equals 6 because 0 plus x is just x. Okay. So basically, again, in word problem ideas here, 0 is going to be the smallest amount of lumens you can have. 6 is going to be the biggest. So therefore, for photosynthesis to occur and stay in our positive photosynthesis, it has to be between 0 and 6. Which means if I were to adjust my graph, I would adjust it to where it would say 0 to 6 for those x values, and then 0 to 700 for those y values, so we can see how high it actually goes. Now, yeah, I could stop at around 650, but I want to go slightly above that, just so we can really see that it does actually top off and you're not cutting off the top too early to see the visual. Okay, let's try another one. So the total cost of producing a product is given by the following function. C of x is equal x to the third minus 12x squared plus 3x plus 9. And that's thousands of dollars, where x is the number of hundreds of units produced. How many units must be produced to give a total cost of $45,000? Now, I'm going to point something out, and it's very important to kind of start to make sure that you're reading correctly here. The function is in thousands of dollars. And I'm asking you how many units gives a total cost of $45,000. Okay. So to start yourselves off right there, first of all, they gave you a function that's always helpful to see, but always make note of what the units are measured in. So you'll notice that when we do this problem, I am not going to set it equal to 45,000. I'm going to set it equal to 45. Now, why am I setting it equal to 45? And again, that's because the problem itself says thousands of dollars, that the cost is in thousands of dollars. So basically, how many thousands of dollars do I want it to equal? $45,000. So I only want to make it equal 45. Now, once we have it there, we do want to make sure that one side is 0, because that's going to be the best way to help us solve any type of polynomial. Okay. So I'm going to set one side equal to 0. And again, all I did was just, let me go back a slide or two so you can see there. Okay. So what I'm going to do is I'm just going to subtract 45 here, and that's going to subtract only from its like term to the 9 there, which is where I get the minus 36. Okay. Now, for many of you guys, if you haven't been practicing your factoring skills, let's start off with let's factor here. Now, this is a slightly different style of factoring. So there's 1, 2, 3, 4 terms. So this is going to take factor by grouping. So the steps to help me do factor by grouping is we start by grouping the first 2 terms together and the second 2 terms together. Okay. Now you'll notice when I say group them together, all I've done is put parentheses around them. There's still a big old plus sign between them because we have not made it to multiplication yet. Okay. I can't just magically change addition into multiplication. That's not allowed. But what I can do is I can maybe group stuff together. And why I want to group them together is I want to see, do these 2 share anything in common? I notice they both have an x in common. Now they don't, there's no number in front of x to the third, so I can't touch that. So I'm going to factor out, say, that should be a power of 2, sorry. I'm going to factor out my x squared here. Again, look for the one that has the lowest power, and that's what they share in common. Here, I'm noticing they both share a factor of 3 because 36 is divisible by 3. So I'm going to factor out a 3. So this one, I'm going to pull out my x squared. This one, I'm going to pull out my 3. And when I factor out my x squared here, that's going to leave me with x minus 12. And when I factor out a 3 here, I'm going to be left with x minus 12. Okay. Now, the whole goal when you're doing factor by grouping is for these 2 items still left in the parentheses actually match each other. So you'll notice the two separate parentheses do actually match. And if they do match, what you're going to do is you're going to pull that whole thing out. And that's going to be my first factor. And what's left in front of the parentheses will be the other factor. And now you've got it in a beautiful factored form that you can continue to solve. So I'm going to set each one of those factors equal to 0. So the first one is x minus 12 equal to 0, which again, I'm just going to add my 12 over, which is going to give me x equals 12. The other one is going to be x squared plus 3 set equal to 0. So again, that other factor. I'm going to subtract my 3 over, which gives me x squared equals negative 3. Now at this point here, remind yourself that this is x squared. This is not, I'm not done yet. I have to say x equals. So the opposite of our x squared would be a square root. And in our case here, that means we end up with x equals plus or minus the square root of negative 3. Now remember back earlier on, we talked about what happens when you have a negative underneath a radical sign. That means we get the imaginary number system coming in. So realistically, we get x equals plus or minus I square root of 3. Now, you can't have an imaginary number as a solution to a word problem, okay? That is dealing in real world, real number system, okay? Again, remember x is the number of units. This is not, we're not talking that this will exist in the imaginary number system. Okay, the only way that you'll have an imaginary number system show up is, guys, if you're in physics, and we're not in physics, okay? So basically my answer is x equals 12. Now remember, x was in hundreds of units. So I have 1,200 units, okay? Now if I were to write 1,200 units out in a number, it would be 1,200. So that's where 1,200 units comes in. And that will give me a total cost of 45,000. Okay. So let's talk about that method that I just used. That's called the root method. Okay, now the root method itself can only be found if you have, say, x to some power equals a constant number. There cannot be any other variable happening there. And again, it's been a while since we've seen the root method, so we do want to keep that in mind. But with the root method, it's really nice because if you have, say, x squared equals a number, you can just solve it out. Or even x cubed equals a number, we can just set that equal to 0 and solve out, and then take a, say, square root, fifth root, whatever root we need to do. So let's look at the root method. So when using the root method, one of the first things that you want to begin to notice is that as you're looking through all of these examples here, none of these actually show anything besides one x value term, okay? So you'll notice that there's only ever going to be one x value term, and then a constant. This is when you know that you can employ the root method. So if I ended up seeing basically like x squared minus x equals 15, then this right here, no, the root method cannot be used. We have to basically maybe use either the quadratic formula or a factoring. We cannot use the root method on this because there's more than one x term. So all of these have to have is one term of x, okay? Now, in order to make this work, we start off by basically taking it and going with that first one there. We are going to just basically say x to the third equals 125, and then whatever the power is on my x, I'm going to take that as the root. So that's going to be a third root of 125, which ends up being 5. Okay, now I'm going to do the same thing on b here. However, with b, before I can actually deal with that root, I have to divide by 5 first, okay? Notice that on this first one here, it had to be x to a power. The ruling says that it has to be x to the power of n equals a constant. If it's x to the power of n equals whatever the constant is, that constant can be positive, it can be negative, it can be a fraction, but it has to be a constant where x has got nothing being added, subtracted, multiplied, or divided, okay? So in our case here, once I have that kind of stuff to a power equals our constant there, then I can do my root, okay? And we got x equals our root, whatever that might be. Now, we have two versions of the roots, okay? There is the nth root with a plus or minus in the front, and then there's one that doesn't have the plus or minus. Now, how do you know which one is which? Because this was a power 3, it's just a third root. But on B here, I'm going to start by dividing by 5, which is where I get my 16. But because this is a power of 4, that's what lets me know that I'm going to put the plus or minus in front. Okay, so this is basically when n is even, we're going to put the plus or minus there. And when n is odd, you're just going to just say whatever that root is. Now, in our case here, plus or minus the 4th root of 16, we can take the 4th root of 16. It ends up being 2. Okay, so the last one here, same process. So what I'm going to do is I'm going to start by dividing by 4 on both sides before I even start the whole root method. Okay, that's going to give me x squared equals 18 over 4. Now, you can go ahead and simplify 18 over 4, which will be 9 over 2. But then you're going to have to take the root plus or minus the square root of it, and that will work too. If you wanted to leave this as x squared equals 18 over 4 this way, and then take your root of it in this format here, that might actually be easier to see the simplification of it. The answer here is basically plus or minus 3 over the square root of 2, or it would be 3 square roots of 2 all over 2. And the reason why I say it's this way is, guys, think about it. You can take the square root of 4, it is 2. 18 breaks down to be 9 times 2, and the square root of square root of 9 is 3, and then 2 is going to stay underneath. Okay. For those that get to move up into higher level math, so say you're going to do college algebra or trigonometry or pre-calculus or anything like that, we really don't like actually seeing the radicals in the bottom of a fraction. So this is going to be the answer that they're going to prefer more, is this way here. Okay, so let's try one more word problem, and hopefully this has given you all those different methods and you're really kind of working your way through all the methods here. So a future value of $10,000 is invested for 4 years at an interest rate R compounded annually, and it's given by the following function. S equals 10,000 times 1 plus R to the power of 4. Now we're going to find what rate as a percentage for which the future value is 14,641. Okay, so off the bat right there, let's remind ourselves that we're looking at a compounded annually problem, and we've been dealing with a lot of these in chapter 5. Okay, if you'll notice, most of the time when we looked at these, we solved these all graphically. And that was because we didn't have enough knowledge how to solve them until the end of chapter 4 or chapter 5, when we had dealt with radicals and dealt with exponents and logarithmic, so exponential and logarithmic methods of solving. So you can still use the calculator to solve for this. That's perfectly fine. However, we can now also use the root method that we just learned. Okay. So the first thing I want to do is I'm going to set my future value to what I want it to be, which is 14,641. Okay, now this looks very similar to what we were looking at earlier, which basically is we had some number like this one. And remember, what did I say we had to do first was divide by 5, right? So in the same case here, think of everything in this parentheses as if it was that x. Okay, so if you think of that parentheses as everything that was in that x value there, then we're going to kind of do the same thing. We're going to start by dividing by 10,000. Now, whatever you do, for the love of everything, do not round. Okay, so you'll notice when I divide by 10,000, I got 1.4641. Keep the entire decimal. So if you need to, keep it in fraction form, but whatever you do, do not round this number, otherwise you'll get the wrong answer. At this point right here, I'm going to take that 4th root. Okay, so we have plus or minus the 4th root of the 1.4641. And now that equals 1 plus R. Now I still haven't solved for R, but basically this is 1 plus R. So how do I move a 1 to the other side of the equal sign? We add or subtract it, right? So now let's take our fourth root, and that ends up being about a 1.1 there, so plus or minus. So basically we have, and let me erase this on the other side here, okay? So what we've got here going on is we can see that basically we have 1.1 equals 1 plus r, or a negative 1.1 equals 1 plus r. So now in this case here, I could subtract 1 from both sides, and we're going to get a 0.1 equals r and a negative 2.1 equals r. Again, I'm subtracting 1 on either side here, and this is how I'm getting those two numbers. Now, as I'm taking a look at these two numbers, first of all, I can't have a negative rate. R itself had to be positive because our money was increasing, not decreasing. So we can rule out the negative interest rate. Again, because we said our interest rate was adding in here, okay? So basically it's 0.1, which is also known as 10% if we translate it into a percentage. Now you could have also used the method of the intersection method to solve, and that would work just as well there. Now, if you are going to use the intersection method to solve, guys, do you remember that in y1, you're going to put one of the functions, and in y2, you're going to put the other one, okay? So in this case here, I put in y1, and then this one here, I put in y2, but it does involve a lot of adjusting of the graph to visually see it. So you'll notice I actually had to basically adjust from 0 to a 0.3 for the X values, and then 0 to like 18,000 on the Y values. So is it possible to use a graphing calculator? 100% yes. Is it practical? It depends on how well you are with your graphing calculator. Okay, let's try another one. So the annual number of arrests for crime per 100,000 juveniles from the ages 10 to 17 years of age can be modeled by the following function. F of x is equal to a negative 0.357 x to the third plus 9.417 x squared minus 51.852 x plus 361.208. Now, X is going to be the number of years after 1980. Now, the number of arrests per 100,000 peaked in 1994, and then it actually decreased. So we're going to use the model to estimate graphically the year after 1980 in which the number of arrests fell to 234 per 100,000 juveniles. Now, a couple of things that we want to kind of note here is they gave us a function, so hooray, we always love it when they give us our functions, okay? The second thing I want to note is basically I'm asking for the number of years after 1980. So we are looking for X, which means this 234 is actually a Y value, okay? So since it's a Y value, I'm going to set 234 equal to our function. Okay. Now, when I look at this straight away, I'm beginning to start to think about, I'm going to have to solve this equation. 234 equals our function. Now, I can use factoring. However, this is going to be really hard to factor because every single one of these numbers has a decimal attached to it. So since it's got a decimal attached to it, I really don't even want to do factoring at all. Okay, because it's going to make it a little bit harder. So that means, let's see, can I use the root method? Well, no, I can't use a root method because I've got 1, 2, 3 terms that have X in it. So since I've got 3 terms that have X, that means the root method's not going to work. Okay, so what other method do I have? Well, if I can't solve this really nicely because it's not quadratic, so I can't use a quadratic formula, I can't really do the root method because it doesn't meet the requirement of what the root method looks like. I can't use the, well, I could, but it's going to be really hard to do the factor by grouping. So the easier method that might be helpful is use the calculator, and we're going to use the intersection method. Okay. So with the intersection method, remind yourself that basically you're going to put one side as y1 and the other side of our equation or our function is y2. And it doesn't matter which one is y1 or y2. So if you want to put the function as y2 or y1, it's your choice. And if you want to put the 234 as y1 or y2, it doesn't matter. However, what does matter is we're going to need to make some adjustments to our window. Okay, now you guys can see this is what the calculator looks like, and this is where the intersection is going to occur. But how do I know what to adjust my thing to? So remember, X is basically the number of years. Okay, it's the number of years after 1980. So what I'm going to do is I'm going to start by just guessing from 0, and then I've got to 10, but what I want to do is maybe a little bit further there. So I would have guessed, I would have started with like 0 to, I would have said 0 to 10 to start off with. And then my Y values, I would have started off at my Y min being 0, and then I would have switched it to about, say, 300 for the Y max. Now, why did I say 300? Because this right here was 234. So I have to be bigger than it so I can see above that line. Now, could you say 250? Oh, 100%. 250 would have worked just as well here. So 300, 250, any of those will work as long as you're above this, okay? So that's why I could see above this line here. Now, if I had said by 10 there, I would have noticed that, okay, maybe that didn't work as nicely and maybe went to 25 because it was kind of so far over this way that it's going to intersect. Okay, then remind yourself you're going to hit that second trace. Now, once you do that second trace and we look for intersection this time, again, you're going to make sure that it hits on the first curve, the second curve, and then the guess where they hit. And we get basically X equals 20.000. So it's during the year 2000 that we will have the arrests will fall to 234 per 100,000. Okay, ladies and gentlemen, that is everything for the chapter 6 that we will get through. So remind yourself of all the different methods that we did just learn. Okay. Be aware that yes, this stuff does get a little bit more complicated if you have a lot more to the polynomial. But what the big takeaway is that the x-intercepts, the y-intercepts, and solutions of a polynomial equal to 0 are all basically the same method. And we can still solve these polynomials by using those methods that we learned in previous sections, like the intersection method, the root method, the factoring method. All of those are ways that we can help solve it. Okay, so keep that in mind as you're going through these.